Hi friends, welcome back in the series of neural network and introduction with deep learning. So today we will have one case study on image classification. So we'll be using again MNIST dataset. So before starting this video, I would request to please do like, share and subscribe if you have been following this series and you are liking the content. So that will help us and that will motivate our team to keep working on it. So before wasting our time, let's start. So basically image classification is one of the important use cases in our daily life, like automotive, e-commerce, retail, manufacturing industries, security, surveillance, healthcare, farming, etc., and can have a wide application of image classification. So that is basically one part of object detection. As we know that object detection is what? Classification plus localization, right? So here our objective is to build a neural network to classify the image based on the object present in the image, right? So advanced technique for training neural networks. So basically we have weight initialization, we have non-linearity like different activation functions, optimizer with the different optimizer, batch normalization, then dropout. So this is the data set that we'll be using. So these are some labels that we have. So basically each image is 28 pixel in height and 28 pixel in width, or we can say 28 by 28 for a total 784 pixels in total. Each pixels has a single pixel values associated with it, indicating the lightness or darkness of the pixel, with a higher number meaning darker. This pixel values is an integer between 0 to 255, right? So the training and test data sets have 785 columns. The first column consists of the class label and represent the article of clothing. Now the rest of the column contain the pixel values of the associated image. So each training and test example is assigned to one of the following labels. So 0, 1, 2, 3, 4, 5, 6, 7 up to 9, like t-shirt, trouser, pullover, dress, coat, and so on so forth. Now loading the data set. So again the version, the TensorFlow we are using is 2.x. Now importing necessary libraries like matplotlib to plotting our graph, TensorFlow of course, sklearn.model selection for train test split. Now TensorFlow.keras.dataset, import fashion MNIST, right, so on so forth, all these necessary thing. Now we are doing train test split. So x train, y train, x test, y test, taking fashion MNIST dot load data. So x train dot shape, you can see we got the values in our variable. Similarly for x test, y train, y test, right? Now here plt dot image, so x train of 0, so showing the first number in the data set. So plt dot plot label. So here you can see that this is the first number in the data set. So that is 9, right? So this image is classified as 9. Now plt dot am show, plt dot image show, so x test 0, so show test, so first number in the data set. So here you can see that again this is of 9. Now data pre-processing. So first we are reshaping our x data. So xtrain dot reshape, xtrain dot shape 0. So basically we are doing n 2828, that is n to 784, right? And similarly for x test. Now converting y data into categorical. So here of course we will be using one hot encoding. So y train to categorical, so y train, and y test to categorical, y test. Now printing the x train shape, y train shape, x test and y test shape. So here now we have the basic NN model, neural network model. So naive MLP model without any alteration. So TensorFlow.keras.models import sequential, TensorFlows.keras.layer import activation dense, TensorFlow.keras import optimizer. So model equal to sequential. Now model.add dense 50 input shape 784. Now activation sigmoid, and adding these activations with the different these activation with these denses. Now SGD equals to optimizer dot SGT, learning rate we are setting as 0.01, model dot compile optimizer SGD, loss equals to categorical cross entropy, matrix equals to accuracy. Now history equals to model dot fit, x train, y train, batch size is 200, epoch is 100, and verbose is 1. So here you can see that it will run till 100 epochs, right? And the loss you can see that 0.9531, and the accuracy 0.65. Now result equals to model dot evaluate on x test, y test. So you can see the loss we have and the accuracy we have. Now printing test accuracy, so test accuracy is around 63%. Now weight initialization, so changing weight initialization scheme, but scheme can significantly improve training of the model by preventing vanishing gradient problem up to some degree. So here from now create a function to generate a return model. So here we have MLP model. So we are defining the model like model equals to sequential, then using normal initializers, right? So defining and adding all these dense, right, input shape and kernel initializer to our model, like activation sigmoid, again for 50 kernel initializer, HE normal, activation sigmoid, so on so forth, and this softmax of course. Now SGD equals to optimizer dot SGD, learning rate equals to 0.001, model dot compile optimizer equals to SGD, loss categorical cross entropy, matrix equals to accuracy, and return the model. So what it will do when we call this function, so it will return a model. So here you can see model equals to MLP model. So all these predefined of the model will be stored in this model variable. Now history equals to model dot fit. Now we will do the x train, y train, batch size, epoch, and verbose. So here now the model building will again start, and here it will run till 100 epochs that we set. Now result equals to model dot evaluate, x test, y test. You can see the loss we gain during model building and the accuracy. If we print the test accuracy similarly, so we have around 35%. Now non-linearity or activation function, so sigmoid function suffers from gradient vanishing problems, right? Now making training slower, there are many choice apart from sigmoid and 10H, try many of them. Now ReLU, that is rectified linear unit, is one of the most popular ones, so we'll be using with that. So MLP model, again defining the function, again all the necessary thing, and here SGD equals to optimizer SGT, learning rate is this, and model dot compile on optimizer SGD, loss categorical cross entropy, and matrix equals to accuracy. Now model, again we are calling the same thing, I mean this in the same way. History equals to model dot fit of x train, y train, epoch is 10, verbose is 1. So here you can see the evaluation. So we have the loss in the model building around 45% and accuracy is 83. Now printing test accuracy, so this is again nearly 83%. Third thing is the batch normalization. So batch normalization is one of the method to prevent the internal covariance shift problem. So has proven to be highly effective. Normalize each mini batch before non-linearity. So from tensorflow.keras.layer import batch normalization dropout. Batch normalization layer is usually inserted after dense or convolution and before non-linearity. So again defining the model and adding the necessary thing with this, then again optimizer SGD, learning it is 0.001, model dot compile optimizer SGD, again same thing, categorical cross entropy, and matrix is on accuracy. Now calling the model and fitting the model with x train, y train, epoch is 20, verbose 1. So here you can see that the loss we gain is 40% and the accuracy is around 85%. Now test accuracy we have is around 85%, right? Now using the dropout, so again defining the model, right? Dense 50, input shape 784, kernel initializer, HE normalizer, batch normalization, then activation ReLU, and dropout is 0.2. Then again dense 50, kernel initializer, HE normal, batch normalization and activation ReLU, dropout is 0.2, and so on so forth. We are using adding all these things. Now Adam equals to optimizer dot Adam, learning rate equals to 0.001, model dot compile optimizer, Adam loss equals to cross entropy, matrix accuracy. Now returning the model, and again calling the same thing, fitting the model on X train, Y train, epoch is 10 and verbose is 1. So here you can see that we again evaluated this as we have the loss as 39% and the accuracy 85%. So far you have seen that the loss is being decreased, which is good for us or for our model, and the accuracy is of course need to be increased. Now printing test accuracy, so if we get the test accuracy, so this is around 85%. So yeah friend, this was all about this introduction of neural network image classification. So in this notebook, we have covered how you can import MNIST dataset and how we can play around it, right? So I hope you guys liking the videos, and if yes, please again do like, share and subscribe. That is very important for us to grow with our team, right? So yeah, we'll come back with next video. Till then, all the best. Have a good time. Take care.